In this video, we're going to finish up our counting techniques by talking about the subtraction rule and the division rule. Now, both of these directly relate to the two previous rules, the product rule and the addition rule. So the subtraction rule connects to the addition rule. And remember, the addition rule says that if we are given two tasks and we have a choice, there's an or, and you can see that even here, we're talking about or, then you add them together as long as they don't have anything in common. But what if they do have something in common? Well, we use the subtraction rule. We'll have to actually subtract it out. So let's look at an example of that. This, by the way, just shows it in the set notation. But let's look at an example of where we'll consider an or, but they actually do have two things in common. So how many bit strings of length 8 either start with 1 bit or end with 2 bits? Okay, so if we're looking at the bit strings of length 8 that start with 1 bit. Okay, so the first one is a 1, but then we have 1, 2, 3, 4, 5, 6, 7 options for the rest, 2 for each, which means then that we have 2 to the 7 options. So then that means for the 8-bit strings that start with 1, there are 2 to the 7 ways that that happens. Okay, now if we're talking about strings that end with 0, 0, that means that the first 6 of them, 1, 2, 3, 4, 5, 6, are open to what we want, either ones or zeros, and then we end with 2 zeros, which means we have 2 options for all of these, or 2 to the 6. Okay, so 2 to the 6 ways that this happens. Now here's the issue. Oops, I thought I had switched pen colors and I didn't. There we go. So here's the issue. The issue is that they're double counting. There are bit strings being counted up here in this first group that happen to have 0, 0 at the end. And there are bit strings in the second group that happen to have 1 at the beginning. So because they're both counting 2 things twice, we're not just going to simply add them together. We have to figure out how many are being double counted. So the ones that are being double counted are the ones that begin with 0 and then have 1, 2, 3, 4, 5 of them and then end with 0, 0. So that means we have, for right here, these empty spots, 2 to the 5 options there. And that is what has been, counted 2 times. Oops, got mad at me for erasing. I'm sorry. Hopefully it all pops back up happy and will not be mad at me much longer. Oops, it is not. It is mad at me permanently. Okay, I don't know why it erased all my 2s, but it did. It got very mad at me. Sorry about that. Okay, so here's how we then use the subtraction rule. So we add the first 2 cases together, but because they're double counting, we subtract out one of the ones that have been double counted, the 2 to the 5 ones that have been counted twice. And let's see, that's going to come out to 128 plus 64 minus 32, which is just 128 plus 32, which comes out to 160. So there you go. 160 possibilities, not double counting. Well, the division rule is the similar idea, except we're talking about product rule now. It is worded a little bit odd, though. If there are n divided by w ways to do a task, if it can be done using a procedure that can be carried out n ways, and for every way w, exactly d of the n ways correspond to the way w. So it's this idea that somehow, again, we're double counting. Let's look at an example of the double counting. Let's say we're interested in seating 4 people around a table. And if 2 seats, or I should say a seating arrangement is considered the same, if one person, when each person has the same person on their left and their right. Okay, so if we just looked at all the possibilities, like if you literally got some cards and put 4 names on them, right? And sat them around a table. So here, I'm going to do that. So here we'll say J for, I don't know, Jose, B for Bob, E for M, and T for, I don't know, Travis. All right. So those are the 4 people sitting around the table, J, B, T, E. All right. Those are our 4 people. And I just rearrange these over and over again. Okay. Let's figure out how many arrangements we can make up. So for the first seat, that'll have 4 different possibilities. 4 different people could sit there. But once that person sits down, oops, in the second seat, we only have 2 possibilities. I'm sorry, 3 possibilities. We have 1 less since somebody sat down in the first seat. So we only have 3 people left for the second seat. And then in the third seat, we only have 2 people left. And then lastly, the last person will sit down. So 4 factorial or 24 different ways. Okay. But the truth is, this variation that I just showed over here is actually the same variation as this. And the reason it's the same variation is that when you look at like T here, T has E on their right and J on their left. And that's exactly what they have here. E on their right and J on their left. So all I did was basically shift everybody over 1 seat, right? I like literally did this. I shifted everybody over 1 seat and it didn't change the seating arrangement when I did that. And if I kept doing this, I would do it 4 different times, right? This would be the first variation, but then the other 3 are going to be the same. So if I just keep rotating these seats, and I'll just write them down just to complete the problem here. So E, T, J, B, and then lastly would be B, E, T, J. There you go. Those are the 4 different rotations. They all count in this 24. They're all counted here, but they're all the same. They really are. They're all the same. So that happens every seating arrangement. I could rotate them around. So I really need to take 24 and divide out the fact that it's rotating around. Those 4 end up matching over and over again. And that really leaves me with 6 seating arrangements, actually unique seating arrangements, switching around who sits next to who. And that's how the division rule works. Okay. Last little bit that they use for counting are tree diagrams, and we will be kind of working with tree diagrams. So that's why we're spending a little time talking about it as an example, where each path of the diagram represents a choice. So for instance, if I start here and I go down this middle path here, that means I am picking, according to this problem, a medium length shirt. And if I go down here in red, okay? So medium shirt in red is represented on that pathway. Over here, this would be a large shirt in blue if I followed that pathway, okay? So all of these represent possible outcomes when we line them up. So you start with the shirt sizes, that's what this first row of dots are, and then the last row are the colors. So we have a total of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And we noticed that in XL and double XL, there isn't as many color options. That does happen sometimes with the larger shirts. So 17 shirts are available. And that's how we can use a tree diagram also to help us calculate how many possibilities there are. And there you go.